Hi, I'm Tom Johnson. Today we're going to talk about the importance of modeling light time delay. So what is light time delay? It's just simply how long does it take a signal to travel from one point to another point at the speed of light. And due to the distances that are often involved in thinking about problems involving space, light time delay starts to become kind of important, and the farther away something is, the more important it is to model. So let's take a look at a typical scenario where here I am on the ground and I've got my little person here and I'm going to move forward in time. So this is my timeline. And this is time as perceived by me here on the ground. Now I'm not actually going to move, I'm going to be stationary. Okay? And I'm going to have a satellite up here in space. And the satellite is, of course, moving forward in time as well. And at some point, what I decide to do is I want to send a signal to my spacecraft and have the spacecraft then send it back down. Or let's say the signal is a radar signal, where I'm going to transmit, it's going to hit the spacecraft and it's going to come back down to me on the Earth. Now remember, the spacecraft is really moving in space, and even though I'm stationary on the Earth itself, of course, is moving in inertial space. It's rotating and doing other kinds of things. So here we are at, I'll call this time of transmit, where I decide to send a signal to my spacecraft. Now, if there was no light speed and everything was infinitely fast, then the second I transmit, the signal would arrive at exactly the same T-transmit that I sent it. It would reflect off and it would come back down, and my time of receipt would be identical because there's no light time delay in this scenario. The signal immediately hit the spacecraft, came back down. Okay? But that's not real. What really happens is this. I'm going to transmit again, time of transmit right here. Okay? And instead of the signal going and hitting my spacecraft at exactly the same time, what's happened is my spacecraft was here at time of transmit, but because of the light time delay, light takes a certain amount of time to get to the spacecraft. What happens is the spacecraft is actually right here at the time the signal is received by the spacecraft. So time of spacecraft receipt, so TSC sub R. Okay? And the difference in time here, this delta T, is my light time delay due to the distance from me on the ground to my spacecraft up in space. Okay? Because the spacecraft is moving. And then when the signal bounces off, instead of arriving instantaneously, it takes some time to get down to me. And this is my time of spacecraft transmit, and I have my time of receipt on the ground. So this is light time delay here, and if I think of it as this is the instantaneous position of the spacecraft at this time, this is another delta T, or another light time delay. So the light time delay is actually affecting us twice, once on the way up and once on the way down. And remember that both of us are moving in inertial space. So it's important for us to model this because spacecraft is moving in inertial space and I'm actually moving in inertial space because I'm on the Earth and the Earth is rotating. Okay? So how big of a deal is this? Well, if I'm talking to an object that's in geosynchronous orbit or geostationary orbit, typically the light time delay on the way up due to the distance is approximately 0.125 seconds. So we have 0.125 up, I have another 0.125 down. Okay? And so our total light time delay is approximately 0.25 seconds. And you can start to experience this if you're doing an international phone call that's being relayed through satellites. Sometimes you can hear a slight delay between the time you talk and it gets relayed to somebody over here, and then they respond, come back. So it could be as much as a half a second delay just due to the light time travel. This really starts to come into play when we start talking about deep space missions, where I'm trying to send a signal from the Earth to Mars, and it can take 20 minutes to get to Mars. And if I'm trying to talk from, let's say, here's the Sun, here's the Earth, and here's Mars, and Mars is way out here, okay? It takes 20 minutes to get there, and 20 minutes to come back. I may actually have to start transmitting even before Mars is in my field of view, in terms of if I've got a spacecraft that's in orbit around Mars. So the spacecraft might actually be behind Mars, but I start transmitting ahead of time, sort of like leading it, like if you're trying to do skeet shooting and you're trying to lead the target. We have to lead the target so that by the time the signal gets there 20 minutes later, my spacecraft is actually not behind Mars anymore. And then the same thing is true when the spacecraft's trying to transmit back down to me on the ground. It has to be clear of Mars and transmit to me and make sure that I'm going to be in the field of view and not going to be rotated out of the field of view before the signal gets to me. So light time delay is important because when we want to do high accuracy analysis, we want to figure out how everything is moving while the signals are traveling. I'm moving in space, my spacecraft's moving in space, and we have to take all the effects into account. Thank you.